Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, good evening, good morning, wherever you are. Welcome again to my Reservoir Lab channel. So today's knowledge sharing will be on short talk about saturation height model from the core and how we're dealing with uncertainty that may associated with the core itself. So in the opening slide, I put two different books as a reference. One is Core Analysis Best Practices, written by the core expert Colin McPhee and Julius Reed. And the second one is Petrophysics Measuring Reservoir Rock and Fluid Transport, written by Jebar Tiap. I think these two books is very popular. I believe we can find something more interested in the book itself, especially in chapter 5, talking about the J function, and the chapter 9, how we dealing and the core, special core for the treatment capillary pressure. These are some of the invented science looking at the scale data continually, and it is like a forensic science in the end, by the way. The talk fits in the quality control measurement of the core. Any kind what we do with saturation height module, assign capillary pressure as saturation height curve to the particular rock property. So let's kick it off. In the case we start traditionally descriptive plugs of porosity, and then if we transform the height to the above free water level for this porosity, then start profiling saturations, will looks like this, and then you go up to this layer, saturation height profile will be like this, and go back again to the lower porosity cross that goes like this, and so on. All those numbers are ways of achieving our target. This is simple, just that single plug represents the start entire porosity links for that doesn't have much heterogeneity. So whatever function we use must be a good fit to the match of data across the entire rock property range. J function as one of the many functions that are used is whatever it is, it has to be good fit to the measurement data, and it has to be able to be easily integrated into something like IRAP, Petrel, Gocad, and so on. We can calculate the volumetric, the number of mathematics available, Thomeer, for example, Haselden, J function, Johnson permeability, power fit function, foil function, Skelt Harrison, Lambda, and etc. And the last one, I think we name it EQR for the quality rocks method. These are all the available functions, and no one is better than the other. This should be fit perfectly with particular lithology to the particular rock type. So why do what we want with capillary pressure? Well, we are easy enough to believe squiggly lines versus depth and don't believe in logs. Then you can't get the saturation height model from the logs. The saturation, the height above free water level, and we have a big advantage at this. They are continuous over the reservoir interval that you have. But number of caveats, such as borehole condition, effect response, we see a lot of uncertainty in the SWRG parameter. M and N electrical properties, or Wegman-Smith parameter M star and N star. The presence of the thin bed, normally you could affect the saturation in a matter of bed boundary, a very thinly laminated sand. It's become a big challenge. Core and I think capillary pressure may decide island choice of core analysis, where one of the core analysis to take the desert island, it would be capillary pressure, because it gives you a direct link between physical measurement of the rock quality, permeability, porosity, pore size distribution, and capillary pressure behavior. But there are uncertainty. There are run logs, there are run core, and the biggest uncertainty, how good is the core data, how reliable is the core data, and what are the uncertainties associated with the measurement. The biggest thing all of that come up to apply in this thing is IFT, interfacial surface tension, just because it's kind of ignored in core labs. But this is when you come into implement this, it can make it a big challenge in terms of reliability. Now, we will go through these are various picture of the equipment tool for mercury injection, capillary pressure. So we have capillary pressure. They are good for low permeability and clean sand as a capillary pressure tool. Perhaps it's not a capillary pressure test because no wetting pace, no strong wetting pace, and no irreducible water saturation. It's kind we assume that all of this data analysis need to be corrected for closure effect. And another effect, for instance, of a burden as well, ugly centrifuge. Well, I call it's good, good ugly for many rock types, but the biggest thing we can buy for this data need to be corrected. We can do this overburden, and then some lab, in particular different countries, they did into the reservoir condition as well. The porous plate, well, I think it's good, but I think it's only good for the high permeability. It's take a long time to do, and in general, most of the laboratory have a pressure limitation, as some lab expert mentioned about the high pressure plates that are coming in. We used this recently, very successful, but these are some of it, not a single test in my view. One of the problem when you see it, particular to take at ambient ones, the overburdened one, and we often face we call a legacy data. That is quite many years ago, almost certainly I think pre-1990, and all had been done in ambient condition shell, and in which we use acute test, the porous plate. They are manufactured by one company called Soil Measure, who's to develop this curve of the brewery and substitute a filtrate all a particular selected material for teasing about this treat without using soil mechanic labs in the core analysis. The key thing about this for the product variable to the brine nor air to oil, the pore size should be smaller than porous rock. Otherwise, adjusted capillary pressure contact medium or N to porous plate that will prevent drainage of brine. So it has to be carefully chosen. And in the old days, sometimes I had to lead weight in addition. Some lab use a mixture, a castle garbage. It's kind of clay material that goes between the porous plate and the core plug itself, just because the porous plate is quite rough and we need something smooth capillary contact. Again, the pore size should be smaller than the pore that contains a container with adjustable irreducible water saturation. Nowadays, we tend to do this overburden, confining pressure to ensure better capillary contact and wettability with higher pressure plate. But one of the key things is what happened in all data sets when you lose capillary contact. When you lose capillary contact, I mean, in other words, when air get into the plates and or this contact medium, and this is kind of example, one of the field in the North Sea. This is capillary pressure as a function of water saturation. These are real air mercury which has been converted to the air brine, and these are all porous plate measurement. And exactly the same pressure falling off the old just kick out, and that what's happened when you get sure that there is no way it's for the water to go. You increase the pressure of the saturation doesn't change because it can drain through the plate. And that is very characteristic things to look for. what astonished me when anything else in why did nobody look at this right and nobody decide maybe the porous plate was not a very good method. In this case of the lab method wasn't very good. And so basically petrophysics, nobody spotted this for years and years. But anyway, that's it. Maybe the porous plate in the case may not be good. It might be ugly because that's how they used to do it. The other issue that you often find with porous plate is a particular ceramic plate. The permeability is very low. It's almost microdarcy. And as you drain to low and low, water saturation, that relative permeability of brine paste become lower and lower. So basically, you must allow sufficient time to achieve an unsteady state of the equilibrium. And this is water production of water saturation for different capillary pressure state. As you can see here, these were run and monitored regularly until they were very short of the equilibrium. A steady state has been reached and then they apply to the higher pressure. So that has been monitored continually. Notice it's about, I think, 180 days, which is a half year. Okay, so this test took about half year to run. In that case, this is another method used by the lab. And we show that recently for somewhat what we are doing this year in situ saturation monitoring during the porous plate. And to do that, you dope the brine with X-ray of gamma ray absorbers such as sodium iodide. And from that, you can measure if you fire gamma ray at it, and you measure the absorption that can translate to saturation. So this gives you basically the saturation profile. This water saturation decreasing here at different capillary pressure. And the good thing about the porous plate is that pretty uniform. Might take a little while to get there, but it's uniform. You can tell the uniformity of the saturation. However, I'm sure that a core expert mentioned that are we safe to use the in situ saturation monitoring for porous plate test? And then it will add a significant amount of cost. So the higher permeability, the higher bound number, and there is rule of thumb, but not much, rule thumb, but there is been work done that say once you get above 10 to -5, you got some unusual effect. So that's something else need to be considered. This is another one. This is what we talk about, and what I really like to see from another coring expert presentation is provision of saturation data for the average of the core. So this is your average water saturation. This is your average saturation, and this plot here. This is hard labor interpretation. Now it's just method of solving this. And the end, we do have Tim Conway calls as dyno, in which we take the core and extract the water by boiling it out. And its called is Dean-Stark apparatus. That gives you an independent check of your calculated water saturation. Depend on how you are going to use the sample afterwards, but generally, that's the kind of thing you might want to add at the end of the test. So that match very well. And this is why when you are doing this, what you need the average saturation, because this is the samples looks okay, and the sample to the curve cross that physically impossible, because in this equation, the change in saturation as you increase the pressure is negative. So the inlet phase saturation must always be less than the average actually at the beginning of the course, and at the end of the course in the middle. there is this called a crisis, and tells me there is something really wrong with the experiment. And the second things I would ask, why you get such smooth less than the curve. So it's telling you again, probably is part of the quality control. To illustrate the effect of that what we are talking about in different analytical methods, the right was no standard. FOB has been probably attained the kind of gold standards in many labs. Now, this was a part of an audit we did have in 3 labs somewhere in Europe. What we did was start with the capillary pressure data set, just took a curve, we back calculated the spin speed. Now they are also faster centrifuge spin for each different capillary pressure. And then we calculated to change the saturation of what the volume would be, and we gave that to the laboratories as set of kind piezometer data. We also added very quite small but fairly typical experimental errors in terms of how accurately can measure the spin speed and how accurately you can measure the end of average saturation as the 3 different labs to process the same data set. So that we didn't ask them to do the experiment, but just a process. This result, so this red line is true capillary pressure curve is inverted comma. Then the other colors is from another lab B, which is used from what we introduced an error. So again, if I can repeat what I mentioned earlier, the result, so this red line is the true capillary pressure curve in inverted commas. The green line is lab B, which used from and we introduced as an error. So there is some uncertainty, but it's interesting how different labs approach. There are some labs see particular just to ignore it and actually shifted the data to what they thought looks like a good curve. But the illustration is that the range of uncertainty potentially by using different method by how you're smooth the production data. So it is important to recognize that, there is a biggest issue with the centrifuge of one of the biggest issue with the centrifuge, the state of data reduction, data smoothing inlet phase calculation. And then we talk about the mercury injection. It's mentioned that I believe this is an old style equipment. This was handed operated a mercury injection pump. Your sample is put in here. And the old days we went to 2000 psi, maybe 3000 psi. We measure pore volume from the helium. And the wetting phase saturation is calculated from the volume of mercury injected. All very kind of period actually is very basics. Now we got something better, and this is a micromeritics auto pour. Then if we move about, because moving target is very difficult, this microanalytic micro auto pour have been taken from the website characterizing material porosity by applying various level of pressure to sample master in mercury. The principal application for pore size and pore size distribution of paper, catalyst, and ceramic, and microanalytic website, it doesn't mention about the core itself, but it's used to core as well. So its primary application, the pore size, the pore size distribution, and this calculator use, I think Laplace equation. This is core experts say that he show us what the slide telling us is basically we put the sample into the sample chamber. We inject mercury by looking at the capacitance difference between the mercury, the metal sheet, and the penetrometer and the mercury in capillaries. Then we can calculate volume hugely accurate to the microliter. we can go up to the 60,000 psi, which is about 30,000 foot oil column. But the biggest thing is sample size. Most penetrometers are this maximum sample size. You get about 4 to 11 millimeters. Typically, output again are very similar to what we saw. Basically, pressure here, the saturation. We asked the laboratory in the case to report of the porosity. This is an entrant. But the biggest thing is sample size. Most penetrometers have the maximum sample size. You got about 4 to 11 milliliters, and the typical output is very similar what another coring expert mentioned. Basically, pressure here, the saturation, and we can ask the laboratory in the case of to report the porosity as the entrant. So the porosity of entrant is here, as we can see in this slide, and that's the plug porosity. So these two and a half, those two unit different between sample engine and the core plug. In this case, the sample bulk volume, which is 4 milliliters. So notice here, there is porosity different. Apparently, a very small bulk volume in my analytic also spit out what we call a skeletal density, which is broadly equivalent to the grain density. So that's something very useful to ask for, because that should be very close to the measure of the grain density of the plug. I think this is the typical data. So this is the injection pressure versus volume. This might be an entry pressure of the closure correction. That's one lab interpretation. Might interpret here subjective, but having this data allow you to make your interpretation. Eventually fill the pore volume with mercury at around 25,000 psi, and the curve become asymptotic. So your pore volume here is mercury filled pore volume, which was 0.6 of millimeters for this sample. And again, I think now it's about the size meters. If we take an inch half by 2.5 inch plug, that's how we used to do it, the porosity about 20%. Then your pore volume with 14 cc 4 inch by inch plug, it's about 2.5 cc. For typical mercury injection sample, it's 1 cc, and so it's 14 times less pore volume. This is typical of what we see with the microanalytic system. No rocks, you don't see it, it's clean sand. You don't see it too much high permeability sign. You don't see in carbonate, or you don't see in particular it's kind of sandstone with clay and micro porosity. So this is basically the blue point here represent core plug measurement made in 1984 by mercury injection using the old style hand pump. Was a big sample. This is a centrifuge. One of just converted them to the same capillary pressure, and that's I think 2008 capillary pressure. It's the same formation. It's not exactly the same plugs. It's the same formation. What this means that if you plot the irreducible saturation set, those as an equivalent first for this data set, it looks like two completely different rock types. So this is rock quality. That's what saturation is. I'm not assuming work. You'll see this all the time. We have seen an excellent agreement, carbonate, excellent, but it appears to be related to the clay content. It's a bit like driving a truck through a cornfield where clay has been forced against the pore walls. And sorry, and I think what happened here is that, high IFT force cause clear destruction as we get to the progressively higher injection pressure. But remember, we used to stop at 2000 psi. Now we go to the 55,000 psi. And I think this result is opening up the pore space. So your pore volume, your sample actually changed during the test potentially. Now we are working with a couple of the labs to see if we are going to be looking at this a little bit further. But what I'm saying is we would be ugly for capillary pressure because of this effect. So if we don't feel unstable, why do we just not use this new incidence? We go up to 2000 psi. If you go to 2000 psi, you rely on your helium core or volume measurement. This curve, where it's not the sample size, it's actually to the entrance from the same plug, where the pore volume is measured using helium, and the pore volume are determined by the volume of mercury filling the pore volume. So if you go to 2000 psi, if you go up to 2000 psi, you don't get an accurate pore volume. It's a bit difficult to measure the accuracy of required because you are dealing with a very small sample. So that's your curve using helium. That's the curve using mercury. So repeat test. Repeat test to another end from the same plug. And then we come to the other bit that people will not want to use in terms of how you apply this. You can compare the data from different labs and data from different systems. Converting to the reservoir condition, all by scaling by the ratios of sigma, cos theta, where theta is the contact angle. And we are assuming that most of your gas reservoir, that's going to be pretty little, probably water wet sigma interfacial tension. So we can scale from oil water to air mercury, or we can scale from air brine oil water, and we can scale to the reservoir condition using this equation here. And once you know, we can calculate the height. These are the typical values laboratories use in the industry, used at lab condition, and these are broadly fine in the sense of they are very reliable. So this is a million Newton per meters, which is the same as 10 centimeters. In the context of studying the behavior of porous materials, the different values used for air brine system in laboratory settings, 72 reservoir setting for the gas brine, and 50 72 for the laboratory setting, 50 for the gas brine, and 26 for the oil brine. This value represent interfacial surface tension IFT between different substance and need to be measured. It's suggesting that measure IFT is more challenging than measuring the capillary pressure, which adds to the complexity of the analysis. It's done mainly in PVT labs, and basically the methods hinge on establishing the shape of liquid drop from the end of the capillary tube. That's mouse and another immiscible fluid. And from the analysis, the geometry of the droplet, then you can calculate the interfacial surface tension. And virtually all methods using pendant drop now are based on the image analysis of photograph of this pendant drop. Illustrate that this budgetary period, I think in somewhere in Canada, for the treatment broadly similar epigravity oils and broadly similar mercury injection in variation. But this is typical value of something that you can see the range of potential entity. And to illustrate this, This is very recent work, I believe, done. There is a gas water reservoir, so gas water IFT measurement are done at reservoir condition of pressure and temperature. The gas was actually recombined from DST fluid, and the water was synthetic formation water. You send the same sample to the lab A, and they got up 17 centimeters, and then you send the same sample to the lab B, and you get 2014 centimeters. And then just to illustrate another different in this 30 and 10 centimeters, some core saturation height just in different IFT. In other words, a comparison between two different interfacial tension values, specifically 30 and 10 centimeters for the same core saturation height. The core saturation height refer to the level of fluid saturation within a porous rock sample. That's mention of the different IFT values suggests that the interfacial tension between the fluid in the sample plays a role in determining the behavior and characteristic of the fluid flow. In my final slide, just to summarize what we have, core capillary pressure data available from the three main tests, all can have another issue. So I'm not a great believer in the good, bad, and ugly, but sometimes good can be ugly and sometimes ugly can be bad. There are uncertainty in which you should think about the porous plate and potentially loss of the capillary contact. We don't need to worry about that, I believe. No, when we are using overburden test, that's largely eliminated, perhaps, or not allowing sufficient saturation time. Why is that? Because you have to pay more because you are using laboratory equipment for longer. So I don't think that we pay enough centrifuge. The biggest issue is smoothing the production data. That method used to calculate the end phase water saturation. Mercury injection, sample size, and the new equipment is an issue that can result in this distortion potentially of a capillary pressure curve, and certain rock IFT, you may get variation and the data between lab using the same samples. It's very sensitive measurement. This panda drop method and the above all, before you start using this, your quality fit control of the log data, you have to basically go through this exactly the same thing as recorded earlier. And I'm sure many another coring expert has another things to add on that. I think that's all my short talk talking about the saturation height model taken from the core. And thanks for the listening. Have you enjoyed? So thank you very much and see you again. Wassalamualaikum warahmatullahi wabarakatuh.